Okay, good morning. My name is Andrea Mocci. I am from Università della Svizzera Italiana, the Software Institute. I'm going to talk about metaprogramming. The title of this talk is Eternal Sunshine of the Spotless Macro. So here's an Escher painting. I'm going to maybe explain better the metaphor that maps it to the title of my talk. So the talk will be about macros. But before arriving or explaining exactly what are macros, maybe I can ask you, do you raise your hand if you know or ever used what a macro? Okay, that's cool. But we start from a more general point of view, which is metaprogramming. So what is metaprogramming? And here you see one of my favorite Escher paintings on drawing ants. And it's kind of clear what the metaphor is here. It's a technique, metaprogramming, where programs have the ability to manipulate other programs as their own data. And that's pretty much any case in which you have a program that can read, analyze, transform other programs in any form. This is considered typically a form of metaprogramming that can be done at runtime, at compile time, or both, and a combination of the two. I will see in this talk how does it look like when you have a combination of the two. The language in which a metaprogram is written is called a meta-language. There are plenty of meta-languages that are not general-purpose programming languages. If you come from the Netherlands, you may have heard and you've maybe done some research or studied there. You may know a programming language called Rascal, for example. That is a case of a meta-language. The ability of a programming language to be its own meta-language is called typically reflection or reflexivity. So this is kind of different with other usages of reflection that you might have heard, but this is like the researcher point of view from this perspective. So if you see the history of metaprogramming over until 2019, this is coming from a survey, you will see that actually the history starts quite early in the history of programming languages, obviously with the programming languages like Lisp. And then you see things like M4, Smalltalk, scheme macros, aspect-oriented programming. All of these are techniques that more or less are linked to the definition that I gave it to you, including Java notation processors. So the topics that I will cover of the different metaprogramming model are these four. We start with the reflection systems. We go through meta-object protocols. We go then into generative programming, and we end up with macros with some bonus at the end. So let's start with reflection system, because I told you what is reflection, but how does it look like a system that actually has fully reflection in itself? So this is supported when a programming system can reason about and act upon itself, modifying its structure and possibly the behavior, typically but not necessarily at runtime. So reason about and act upon itself. What does it mean? Well, typically you have two aspects. One is introspection, which is the ability to examine its self-representation, and the other is intercession, which is the ability to modify it. Both of them can be there or can be not. Another, and we will see, another dimension is structure versus behavioral. You can reason about the structure of a programming, like of a program, like if it's an OP programming language, then you would have classes, methods, and attributes. You can inspect them. If it's behavioral reflection instead, it's more the kind of thing that is subject here is the dynamic relationship between objects. It could be the object class relations, pointers, whatever. So that's a fundamental distinction. So I can show you, for example, how does it look like in a programming language where you have all of this. Let me see. There it is. So this is Smalltalk. Have you ever written any line of Smalltalk in your life? Yes, at least one person. Very good. So here, this is like a live environment. So when I'm going to execute this piece of code, which just creates a new object of this, of a game in this case, I would be able to inspect it. I have this notebook-like interface, which is kind of cool. So then I can access the class. This is very similar to Java reflection. I can access an object that represents the class, and here it is. And after that, I can access with another method, which is called methods, the list of methods of, whoa, the list. Did I execute this? Yes. All the methods of the class. Voila, all of this. And I can inspect, this is like a map, the lines of code for each one of these methods. Each one is different. Some of them have 2 lines of code, some other 27, and on average, it is 5.52. Very good. This is like structural introspection. I can do also dynamic introspection. I can, for example, take a special object, this context, and inspect the stack, okay? And here I would see the stack, all the methods that are in the execution stack of this particular notebook cell that I executed. Or I can take, for the code I'm executing, even the code itself that is being compiled. And this is the typical aspect of introspection. With intercession, you can do something a little more interesting. Here I'm taking an object, which is the top class, more or less, like in Java, and I can create a subclass that I call Hello World. And voila, I get a new class. I can inspect that, and I can compile a method on that. I pass, actually, the code of the method as a string, not very convenient, you will see how, because there could be syntax errors there. I would get an exception out of it, but that's it. And I can now create a new object of that class, whatever. That obviously answers to the hello message, so I get a string out of it. Something that I may want to do is to add instead this method to a single object. Do you think I can do that? Well, let's try if there is a method compile for the object. It's not there, and we will see these methods a lot, so I get pretty much an exception. Not really, but it's most like that. So imagine now I create another object, which has no type, it's just of type object. I try to call hello, obviously I get an exception because this method is not in the class. But what I can do, and this is something that pretty much only Smalltalk can do, I can change the class of that object at runtime. Now I change it to the hello world class that I created before. So this object now is of type hello world. And now that object will answer to hello. You see, I'm not rebinding a variable here. I had an object and say, oh, now your superclass is going to be hello world instead of object. So your class is going to be that instead of that one. And you can do all the kind of crazy things with a system like this, where you have a full intercession, even at the dynamic level. Just to give you an idea what kind of features you can get when you have full reflective system like this, based on Smalltalk. If you're curious about it, download it because this system is amazing. Written in Pharo, so Smalltalk, and often in Rust. It's quite cool. So here you see the kind of types of introspection, intercession, structure, and behavior that you might have in languages. Obviously, Smalltalk and Lisp are super cool, so you have all these features. In Java, you only have structural introspection. So you can, for example, given an object, get an object that represents its class, then get the methods and stuff like that. But you don't have any form of behavioral introspection, structural intercession, and you have a little behavioral intercession, but that's kind of a tiny little piece. Ruby is almost as cool as Lisp and Smalltalk, almost. Okay, this is all on reflection system. Let's talk about meta-object protocols that I actually already used. So a meta-object protocol are the interfaces that allow access and manipulation of the structured behavioral objects. These describe the meta model you have on the meta side. So in this world where object represents program elements pretty much. And here it depends on the actual meta model that you have on that side. There are two classes, actually. There are more, but the two most common are two families. And these families actually will allow you, in the way you use it, even to transform the original language behavior and to customize it really deeply. This is what you normally do with Lisp, when you can create custom languages, and even in Smalltalk, okay? And the typical reference meta-object protocols are these two. So a typical structure similar to the one I saw you before is this. On the base level, you have your objects, the one that you normally manipulate. When you go on the meta level, you have object that represents class, and these are instances of a type that is actually the meta class, okay? And that is responsible of all the behavior of the object system, okay? So, for example, you can have methods that create new methods, or methods that modify existing method code, change the class structure by changing the inheritance, all of that stuff. And this is typically, typical. But this is not the only model. Another model, which is the one of Ruby. Have you ever programmed in Ruby? Just raise your hand. Okay, 3 people. Here you have a meta level which is different for classes and objects. So it means you have these eigenclasses. You can have an eigenclass for a single object, and you can have an eigenclass for a class. And that represents the meta level when you can have modification. So let's have a look on how it looks like in Ruby. Let me pick it up. Voila, this is DSL, this is Ruby. So imagine you have a class, I call it lupus, that can woof, pretty reasonable, right? And I have a method which is called make me quack, which will take the eigen side, so the meta side, or whatever I pass it, it can be an object or a class, and would add a quack method. Here you see something different. Before, when I wanted an extra method on an object or on a class, I pass it a string. Now I'm really having just code, and this is like how awesome Ruby can be. So in the main here, I have a lupus, another lupus, so 2 wolves, and I can try to make quack the first one. So I can call Ruby on eigenclass .rb, and the first wolf will respond to quack, so it quacks. And the second one doesn't respond to quack because I made quack only the first wolf. Okay. So what happens now if I pass a class? Do you think both lupus, so both wolves, will quack or not? Raise your hand if you think both will quack. Okay. What they think the opposite? Nobody. Okay. Let's see. Both of them do not answer to quack. Why? Because I added the method to the eigenclass of the class. What I have done is not added to all the instances of that class. I added at the class side, so pretty much I added a static method. So I can put as lupus.quack in this way, and if I run it, I get a quack, but from the class. So here you have 2 different, completely different meta sites for objects and for classes. There's always a way to make all of them quack, but it's different, and it's using class-side evaluation. It's a different meta concept. Okay, so this is like a different object, meta-object protocol. Let's talk about generative programming, which is like up to now, I'm talked about mostly about how to operate between objects at the meta level. I want to now talk about manipulation of code. I added just a bunch of new methods, but can I change the behavior of the methods by changing the code? And this is what is generative programming about. You have programs that manipulate and generate other programs to some algorithm and on a program representation. So imagine you have objects. They represent an abstract syntax tree, and you can manipulate them, and you have a distinction normally between normal code and meta code, so the code that operates on code. The typical approaches are based on AST transformation and compile time reflection, and if you have ever seen a Java notation processing mechanism, this is exactly what it does, but it does it in a very primitive way if you want, because with a Java notation, you can inspect the code, but in order to change it, you just have to generate some text of the generated code. The systems, like the one in Groovy that I'll show you now, they actually operate they actually provide full AST creation facilities, and so quite a complex output that you can get, which is transformed source code. These are normal objects that get compiled and interpreted actually like normal code. Let's see how it looks like. So, well, this is a spoiler. I have this with logging method, with logging annotation, which annotates this method and does something. When I run it here, this greet method is supposed to just print hello world, but when I run it, it will do two things. It will add starting greet and ending greet. So it added two statements that print line the beginning and the end of this execution. This is very trivial. You can do obviously more than that, but let's have a look how it looks like. So this is an annotation that actually, it's a Groovy AST transformation, which has a visit method inside that provides you an object representation of the code. In this case, you can retrieve the method from the nodes, and you can, for example, add two print line statements. Now I have an utility method that creates those and adds them at the beginning and at the end of the block. So here I have object that represents program elements, imagine like an AST, and you can insert them on the code. This is pretty cool. So for example, how does this look like? This is like any other expression. If you ever used ever seen the internals of a compiler, or maybe you've done in the past a course on languages and compilers, this is how it looks like. You have a statement, and you have a method call expression, you refer to this, then you have the name of the method, and then the arguments. And you construct a little AST that you can compile, actually, that you can then interpret, and it can get executed. And this is added at the beginning, at the end of the block. Obviously, if you have multiple return statements, this will not work in this particular way. You have to be a little more smart when you visit, but you get the idea. So here, I'm inserting code, not like I've done before with a string or with real pieces of code, but by adding, an object that I construct like an AST. Good. Whoops. Okay, so this is like how it works in Groovy. Can you do better than that? Well, the answer is yes, and you do it typically with macros. When you have this combination, and you blend the two worlds, the meta and the normal level. So macro is in general a pattern that specifies a certain input sequence get mapped into an output sequence. As easy as that. So the process that does this transformation is called macro expansion. This is not just a transformation. It's something that can be more complicated than that. It can be, for example, recursive. So the idea is that if a programming language has a macro system, you have something that it's kind of blurred between the meta level. There's some blurring between the meta level and the normal level. And it typically in a way that is coherent with reflection principles, but for the code. And here obviously, Lisp, and in particular Scheme and Racket, they support all the variants of macros, except obviously lexical, because they are not very interesting. But typically they work at the syntactic level. Modern languages like Scala, Julia, and Rust, they support most of them. Pattern-based is just a different style. But I want to show you now how it works in Scala in a few slides. The others are almost similar, but maybe not that elegant. The only important thing is that when you're manipulating this kind of code with macros, obviously you can have variable clashes. And in order to avoid that, you need to guarantee it through hygiene that you don't have, whenever you expand code, you don't, for example, clash with variable names, because you can introduce new variables. And I'll show you what I mean by that. Okay. The world is now split in this meta and base level. And you have normal code, normal expression in the base level. And in order to go to the meta level, so extract an AST that represents you a quotation. So on the other hand, instead, you can splice a piece of code, and you can go from the meta base to the base level. And yeah, so pretty much a macro would be a combination of these splices and quotation, one inside the other. This expression of T is like if you want something that represents a type version of the AST for your piece of code. And you can manipulate it with splices and quotation. So this will guarantee type safety if it's done well. but you cannot do certain things, like, for example, extract the name of a method as a string and then reinsert in that. That would be not legal. For that, you need compile time reflection. Let's have a look how it looks like. I usually teach this to students in a course of DSLs. And what I do is typically show them how to build a language like this, a very simple language like this. I have a testing, this is Scala 3, by the way. I have a testing framework that I wanted, similar to Scala test, that works like this. I have, I don't know, list 1, 2, 3 should be non-empty. And here what you see in the compiler note that I have up there is the translation done by the macro in an automatic way. This becomes an assert that list 1, 2, 3 is non-empty. So this non-empty is actually a method of the list. So I'm rewriting this assertion, which is fluent, it reads like natural language, into a normal assertion. This is just a toy example. If you don't believe me, this should method has no implementation. If I command click there, nothing happens. But when I run it, what actually happens is that this assertion method rewrites that into the actual assertion that I need. How does it look like? So here is the point where I go from the base level to the meta level. So pretty much this becomes, okay, it takes this piece of code, this AST, that this other method, the implementation generates, and make it a real expression. So I splice it in like I would do with string interpolation, but I'm doing it with ASTs. Let's have a look on how this looks like. Whoops, this is like the wrong one. This is it. Now, it's a method that takes an expression of this assertion and returns another expression of unit. Imagine it like a void, because this assertion do not return anything. So they're just void. They can execute successfully, or they can throw an exception. Very good. So on the base case, this is all recursive, but on the base case, I can use pattern matching to match one assertion as the type that I want. These assertion properties that I described you before. And then with this method, I can rewrite them in a single case. How does this look like? Well, this is how it looks like. With pattern matching, I can say this AST matches any type, an object of any type. Actually, it's an expression of any type. Then the method should, then be, and this with this select dynamic, I'm using a magic to extract the method name with a string. And then I generate the actual assertion. I don't want to go into the details because here I'm using reflection, but the important thing is at the end. Look at this. This is what I return. It's a piece of code that I'm quoting, and this is really an expression that represents the final assertion. The assertion, I insert the call, and then I put the customized error message that I need. So when I'm generating with a macro some code, this stuff is expressed with the same syntax of Scala. So I'm not using strange APIs with expression statement and stuff like that. That I'm using only for more complicated stuff, but as soon as I stay in the world of expression, all of these things can be expressed with code, like this assert, that is not actually executed in this particular point. There is an AST that is constructed, and this is what I get, okay, in the end. When I run it, let's see. When I run it, this would just do nothing because obviously this is executing successfully. If I put it like an empty list, whoops, an empty list, so this should fail now. Yes, I have up here an assertion error, okay? This is executing as I'm expecting because that's the assertion that I actually want. Okay, this is kind of cool. With the macros that you have seen, up to now, the expansion happens at compile time, but nothing forces you to not have this actually happening at runtime as well. Why would you need something like this? Imagine you have this power method, and you know that the exponent is always be an integer. If it's, or maybe it can be something else, but it's going to be, when it's an integer, you want to optimize it and make it just a sequence of multiplications, okay? And optimize it like that. Maybe because you want to reuse it many times with the same exponent. So this is a toy example, but it's using all the metaprogramming things. And I'm going to show you how it looks like. This is simpler than the one before. It's called multi-stage programming. So here I have a main method. When I'm going to read, the first argument is going to be a base to float. The second one is going to be an integer. If it's not, I'm going to crash. This is just some toy code. Then I construct the stage power, which would optimize the power. And then I will execute it. How I'm going to actually optimize it? Now, the stage power is like this. It first constructs some piece of code, and this is the idea, and it will return an expression that represents a function from double to double, from the base to the actual series of multiplications. And this is like in the meta side. And then I can interpret it and run the particular code, okay? This would be my stage power. This would return me a a function from double to double that I can then execute, okay? How does this optimization actually look like? This is very simple. You can almost read it. So if the exponent is 0, you can already optimize it as a constant, 1, right? Except maybe if the base is 0, but. Then if n is equal to 1, you can just return x, okay? Which is an expression, so it's still on the meta level. Let's ignore this negative for a while. If it's positive and equal to 2, then you just return x times x, a multiplication. And if it's odd, you do it recursively. So you multiply a single x with the power code on n minus 1, so it becomes even, and you can apply either this or that until you arrive at the end, which is this. In this other case, what do you do? Well, you have a power of 2, so no, you have anything, a multiple of 2. So you cache the multiplication of x times x, right? And then you reapply the macro on n divided by 2, and so you would have a logarithmic number of multiplications. So you have optimized this into a logarithmic number of multiplications. That's the idea. So let's start with run main. So I will do 3.17. Let's start with 1. So this will compile it, and it takes some time for SBT. It's slow, but you would see both the code, which is the optimized code, x, and then the result. Now, if I do the same with 2, what do I get as an optimized code? It would be x times x, and that's it, x times x. If I do 8, this is where it's going to be fun. And you will see hygiene playing. I have to always here I define a y. So the first time it's a y, the second time it cannot be the same y, it should be another one. And in fact, what this code is doing, actually what the compiler is doing, it's ensuring that every time I need another y, it has a different name. This is y2. In Scala, you can use with backticks any Unicode, or most of Unicode characters. So this is the optimized code that you can easily read. And this is how it works. Okay. This is quite cool. And now we have the meta level, which also happens at runtime. So this number 8 was only read at runtime. I generate the code, and then I use it. I can reuse it how many times as I want. Very good. So this is what I showed you: reflection system, meta-object protocols, generative programming, and macros. You may be wondering, what about Java? Okay, do you program in Java regularly? Raise your hand. I can see. No. Oh, that's interesting. I was expecting more Java programmers, but now I'm going to give you some news. First of all, do you know what this person is? No? No. So I'll tell you later who it is. It's talking about Java, I think in 1997. Okay.
Okay, and here's the other big source. Certainly the greatest single language, along with Simula of the 60s, I think one with as many profound or more profound insights, Lisp. On page 13 of this book that was published in 1962, there's a half page of code which is the reflective model of Lisp written in itself. All the important details of Lisp semantics and the guidelines for how to make a Lisp interpreter are in that half page. And it is this aspect, this meta-reflective aspect that I think is to me, is the saddest thing about what's happening with Java. So when Java first happened, I thought, well, it's legitimizing something that most people have not believed in for a long time, which is this bytecode approach of being multi-platform like we had at Xerox PARC. It's not a new idea. It actually goes back into the 60s. But when I looked at Java, I thought, my goodness, how could they possibly, and of course, we know that the history was more about programming toasters originally than being on the internet. But my goodness, how do they hope to survive all of the changes, modifications, adaptations, and interoperability requirements without a meta system, without even, for instance, being able to load new things in while you're running. So to me, this is the fact that people adopted this as some great hope is probably the most distressing thing to me personally, as I said, since MS-DOS. I mean, it represents a real failure of people to understand what the larger picture is and is going to be.
So it was complaining about Java lacking a pretty much reflective system, and slowly some things were adopted that actually made most of the modern frameworks in Java actually work as they do. Like, for example, aspect-oriented programming was trying a little to compensate this lack, but also annotations. So if you're using Spring Boot on a daily basis, for example, all of these two major things are fundamental in the workings of a framework like Spring Boot, and any major framework of Java, they use this in any other way. And the important thing, by the way, he's Alan Kay, is a Turing Award winner, is quite important in the history of computing. Look him up. All these talks are amazing. So this is what Java has up to now, just these two systems. A little reflection, some annotation processing, and you can use aspect-oriented programming if you're using aspect-J, which are part of the, not really Java, but you can integrate it relatively easily. But is it that it? Actually, no. There is something called Project Babylon, which is coming up, which is adding more reflective system in Java, and it's super amazing. So it will add reflective capabilities that are able to give you a model of a piece of code. The problem with this code model is that it's not really Java. Java is always unique when it does things. So in this case, it's actually something that is more suited for analysis and transformation, because what they wanted to do is to make it cool for foreign programming models, especially for AI, and that's why the way Oracle is actually selling it. So you can write down, for example, now a piece of Java code that can be interpreted as a GPU kernel or as a machine learning model, starting from Java. And I want to show you how it looks like to finish. Oh, IntelliJ crashed, good. Okay, I don't need IntelliJ. That's the piece of code. So I have this annotation called reflection, which actually allows me to inspect the code of this method with the code model that is provided by Project Babylon. If you want to try it, you have to recompile a version of the JDK that has this, and it's non-trivial, but it can be done. It took me a while. And then I want to show you how this code looks like, just to obviously need to run Maven first and recompile stuff. Yeah, Visual Studio Code is complaining. This is the string representation of the code model that you have. It looks like more like an intermediate representation between the code and the bytecode. So there you have, for example, explicit invoke for methods. You need to load sometimes the variables. So it's a little lower, not exactly high level as Java code. It's a little lower level. So what can you do? Well, you can actually do the same transformation that I've done before. You can get the code model, and you have APIs to transform it. Up here, for example, you would see a switch on this OP that can be used to traverse the code and replace stuff. I can show you now. I have maybe just a couple of minutes, so I'll leave it for questions. If the exponent that I can retrieve is constant, so it has a value, and it's equal to 0, then I can create a new node, which represents a constant of type float equal to 1.0, and I can replace the thing that actually was the math.pow. Let's see how it looks like if I re-invoke it. Up here, I have 1 as an example, so I already have it rewritten down here. You have here a conversion of this constant into double and just returning it. That's the new implementation of the method. The other is loading the base for no purpose. I should have also tried to remove that. So if now I put a 2, the code is really ugly because you need to do it in a procedural way. So I'm not proud of it, but if you want in the question, I can show it to you. And now, just to give you an idea how it looks like, I assign it to a variable, and then I multiply it, and then pretty much return it, okay? When you want to do it the most general way, with like 4, whoops, it would look very similar, but with 2 multiplications. The Red Hat language server complains because the versions are not exactly the ones it would expect. You have the 0, so pointing to the base and multiplying it, then it would store into a variable, and then multiplying it again, and then returning it. So the API resembles more the one that you would have in transformation of ASTs in Groovy, but it will allow you to do super cool stuff. This is pretty much the core of the code, where while the exponent is not equal to 1, I would add a new multiplication node and add it inside this transform code, and in the end, replacing the math.pow call. So this is it. I have maybe 2 minutes, 1 minute actually. I'll show you all of these metaprogramming models with different languages. If you want to try something cool in your Slack time, this is probably something where you open a little your mind and would be super cool. Thank you very much. If you have maybe just a quick question, otherwise I'm around until tomorrow. Thank you very much. I'm Andrea Mocci, and this is Eternal Sunshine of the Spotless Macro. Thank you very much. Maybe one question if you have it. No? Oh, yeah.
About this kind of metaprogramming, the typical problem is that the generic code is difficult to understand. You don't have an overview, it's difficult to debug.
Yes.
Is there a way that is solving this?
As far as I know, no. The only thing So debugging is extremely problematic because, for example, when you do the expansion, you're actually during compilation, right? So the best way for me in Scala to debug, it would actually to do the very old style of printing the code that I'm generating. The cool part is that in that case, I can generate compiler reports. So for example, I can generate a .info, an information, the blue thing, or like a warning from the compiler that would be seen in the IDE, so I would understand what is actually happening. So what I showed you before here with Scala, in this particular case, this blue line is actually a compiler message, right, generated by the macro, and this is extremely helpful for me because it's giving me the translated code up there. And this is not some magic. There is a piece of code in the macro that would generate this message. And this is typically the best way you have it to debug it a little. But breakpoints and stuff like that, I am not aware, at least in Scala or in Rust, of an easy way to do that. So debugging is still an open problem. Maybe even a PhD topic, if you like programming languages.
The idea is that you need to debug also the metaprogramming. Apart from the code that will actually run, also you need to debug facilities for...
Yes, exactly. That's what I mean. At the moment, they do not really exist as far as I know. Okay? Well, thanks again.